So I was saying we're going to be talking really about using query-based language to sit on top of a key value store and understand getting data out and manipulating it in the normal way. Although I'm talking about work that's happening on the Riak Time Series system. Lots of people have. The core team's quite small, but a lot of people have done some work, so it's not just me. Okay, so SQL and NoSQL, a match made in hell. Putting a SQL query language. You ask why do people tend not to put SQL in front of key value stores? And the reason is there is actually a very solidly supported dialect of SQL that you can use in key value stores. And it's kind of a Model T version of SQL because you can write any query you like as long as it looks like that. Select key and value from table where key equals some value of a key. So there's a reason why NoSQL has no ability, because typically in a key value store, you're trying to solve a totally different problem. You're trying to solve problems of availability and living with partitions, and you're not trying to solve the problem of actually manipulating the data. So you tend to use a key value store as a fairly dumb object that you put in, a fairly dumb store that you put in objects that may have some structure to you, and you then deal with them at the application layer. Because it's a Basho talk, you're obliged to have a picture of the ring, but the problem with the Basho ring is it's a pain in the neck in slides, so my ring is flat, so I thought you're all good scientists, you can all understand and conceptualize that rings may not be round, but I'll give you a picture of Saturn's rings anyway. What I'm going to do is I'm going to talk you through some of the aspects of the problem that we're trying to solve, trying to get away from, where we need to use the underlying properties of Riak to give us the reliability and the availability that we need, and then try and find ways to then put data in that structure in a way that allows us to move the querying and data manipulation from the application into the database. So it's a classic engineering problem. You offer a service at a layer, you look at what people are building above that layer, they build all sorts of complicated things, and then you say, actually, if we take that work that everyone is reinventing and push it down below that layer, then we increase the utility of our surface customers. And Time Series is kind of part of that world. So this is my poor man's version of the Riak ring. How a KV store typically works: you store more than one copy of data, and we use a hash function to get there. We have a key at the bottom, we push that into the hash function. This is a pretend ring of 12, and it resolves to a value 3, and then I write Alice to a logical position in this ring, and I write another couple of issues. So I've now got 3 copies of my data stored on my ring, and I can do the same thing with Bob, and I get 3 versions of Bob. And I do the same with Kate, and you can see it's a ring now because my ring has rolled back to the beginning. So you're all able to conceptualize that this ring is circular, and it's rolled back. So, I mean, there's your fundamental issue of how a key value style works. So what we're trying to do then is, and in this world, we have a key that we put into our partition function, and we have a key that we write on disk. And these keys are the same. We use the same key to hash that we do to refer. So the key refers directly to the value that we've got in there. So what we do, and this ring is then mapped onto physical nodes. This is a 12-node ring. It may be mapped onto a number of servers, and the servers represent the different logical data things are then mapped onto. So typically you may have a big installation with 1,024 virtual nodes and maybe 150 physical servers. So that's how you get your high availability and your linear scalability. You get this sort of logical physical mapping. And if you get the numbers right, then you guarantee that the 3 versions are written on 3 separate machines. And there's a whole world of complication around that's kind of not really that relevant. So the fundamental problem with that model is that you only have effectively 2 data access nodes for querying. If you know what the key is, you can go straight to a typical installation. You might write 3 values of data to Riak, and then you may read 2 back, check that they're the same. So I'm going to pretend here that we read 2 values and check that they're available. So if I have a key, I can then go to 2 of my logical vnodes, which is most cases 2 physical servers, ask them a question, I get some data back. If I don't have the key, then I have to ask the entire ring. And because I'm writing 3 times, that typically means I visit every third vnode. But if I have a big cluster with 1,024 vnodes on 150 machines, that actually means I have to visit every machine, some for a single point, some for a multiple point. So I either say, I get the answer, or I have to ask the ring for everything. And these big jobs where you query the entire ring are a map-reduced job, and they're very, very expensive. So you have this 2 costs of cheap to get one, expensive to get many. And what we're trying to do is infill between those two query modes, so that I can get more and richer information by not doing as little as talking to one vnode and not doing as much as talking to the entire ring. And also, if I'm querying the ring, it's not just going to the physical servers, because when I go to the physical server with a key, I also go to a logical point in my database and get the data back. If I'm asking questions about the entire ring, I'm actually scanning the key space on every vnode as well. So not only do I have more journeys, but I have more work to do at the far end. So the cost of actually doing full query mode is really, really expensive. So you have to try and trade off those 2 things. So if you have a key, you talk to 2 servers. If you don't, you must talk to every server, and you must traverse the entire key space. So what we do with time series is first of all, we break this link between the hash key and the local key. We still need a unique local key so that when we write data, it's to a unique location and can be referred back. And the typical thing we first do with time series then is that one of the reasons we're doing this for time series as opposed to general queryable data at the moment is because time series is a common use case that has a fixed data pattern. So you're actually choosing a subset of data models to implement queryability for a subset of all data models that people normally use. And those data models are typically writing data. It's the same thing but moving in time. So what is the temperature of this industrial unit now? And in 1 minute, in 2 minutes, and 3 minutes. So my blast furnace reports its temperature every 15 seconds. I then have a history of that machine's operating temperature, or a Scale Electric's out there reporting its lap time, or a traffic sensor reporting that it's available, or signal strength on a base station. There's a whole number of use cases that represent the same information traveling in time. And so we're effectively looking at queryability for that data set. We're implementing that for a customer use case, but we're trying to design for a bigger set of worlds. So in this world, what we do is we take a 2-part key, which has an identifier and a time component, and then we perform a quantization on the time, and we use that. When we feed that into our hash function, we get basically, here I'm saying quantize my time in 10-second chunks. So I get a series of readings that come rolling in, and for that 10-second window, I always write that data to the same place. And then I write the next bit to another place, and I write the next bit to the third place. So I now have collections of related data, and they're related by time slices, and they're written in the same physical place. So if I talk to 2 servers, I can then query. If I've got a 10-second slice, I can then query data for 10 seconds. So I make the same journey. That data is located next to each other on disk, so I have a short traversal time, and I'm basically altering the collocation of data to get more richness. And I can as I span more and more quanta, I linearly increase the amount of visits I have to make. So 1 quanta I go to 2 vnodes, 2 quanta I go to 4, 6, 8, 10, and eventually I still have to talk to all servers. So what I'm trying to do now is in that space between do everything and do a very small amount, I'm trying to increase the range of query options that I've got at the cheap end and put some data in there. Now, you are making trade-offs here, because one of the ways in which a key value store is highly available is that the hash function distributes work very, very evenly across your 150 nodes. And once you start quantizing, you start effectively making your data write patterns more lumpy. And if you get it, it is possible to sit and set up a time series database where you quantize everything to write it on one vnode, and then you can access it all, but then you have 150 servers and one of them's busy and the other ones are just sitting there. So there is a trade-off between how I distribute work and how I get access to my underlying, well, we don't have spindles anymore, do we? We've all got SSTs, but there is a trade-off between localizing the data and lumpiness in your cluster. And so effectively, we're using time as a mechanism to collocate data, and then having collocated the data, we then have it in one place, and it becomes effective to write queryable language to access and operate on that data. So as I say, yeah, you have to trade off the quanta versus the lumpiness. Okay, so can we improve that? One of the other things we're trying to look at, so we now have a query thing, and I'll talk about the language in a minute, but we still have this two-access pattern. We still have effectively the same problem. You still need to know enough information to go and get a quanta. So you need to know what identifier am I looking at. There's a whole range of stuff that you still need to know. And at the moment we have inside normal KV we have a thing called 2i indexes, where we effectively have a key space in our ring, and then we have a separate space for an index. And when we write to a key, we write a lookup index into the index space, and we can then query that. We can query those indexes to say, I'm writing. It's a classic index approach. You write it under a primary key, and then you have a second field that you're indexing on, and then you can say, tell me the names of all the master keys, but also matches the index. And that does work, and it gives us a number of issues, but the problem is that we write the key in the index. We write the index value on the same physical vnode as the key, and it's under a single transaction. So if I wish to get a list of all index lookups, I have to do if I wish to get a list of all the indexes, I still have to go and visit the whole ring. I have to go around the ring and say, to every vnode, can you tell me all the keys that you have that match the index? So I still have, it gives me two access roads into the data, but there's still an expensive cost to running an index. So, and we'll talk, when I talk about future work, we're talking about ways can we reduce the cognitive load, can we reduce the cluster load of trying to get index information so that we can look up data. We've all seen Erlang the movie now. We're going to have the sequel. Yes! I get to make bad jokes. So why SQL? The reason for using standard SQL as a query language is because everybody knows it. There's a low barrier to entry. We just saw Fred Hebert doing a presentation about why we made the right choice to use standard SQL as our query language. The barrier to entry for a new developer is really low. You can sit down, you can play with the shell, you can type stuff in, everyone knows how it works. The secondary advantage is that there is good tooling, so people already have things that emit and run SQL, so you don't need to worry about that. And SQL is actually a fairly well it's a well designed declarative language with some key and obvious routes to extend it in a way that doesn't break it. So it makes a lot of sense to just try and use very, very standard SQL. And it's Henry here was saying how I'm a tight Scotsman. All of you will know that we love in Scotland, not invented here. We love when someone else has done the work for us. We love not paying for it. Having someone design a complicated language. There's lots of people who would say, oh, great, let's design our own query language. That'd be cool. We can spend a year inventing something that's vaguely SQL-ish that you can kind of looks like, but uses semicolons, commas instead of, or whatever. I don't like any of that stuff. Somebody's done this, good job. Let's keep moving. So there are good, sound business reasons to use SQL. So I'm going to give you a very high-level architecture of how it fits into Riak. Riak is a complicated beast. At the core of the Riak architecture is the Riak core library, which is a library that manages clusters. It does gossiping. It moves information about, allows a cluster to share state and do share configuration and generally operate as a loose cluster. And Riak KV then is an implementation of a Riak Core application. It sits underneath Riak Core, and it performs core key value operations. And then at the very bottom, you have a number of physical instances of level DB. You have one per physical server, and they are C++ code. They just accept data in, which they then persist to disk and read back. What we did with Time Series is we tried as much as possible to not screw up that architecture. So the Riak query language really sits as a set of libraries that floats over KV. We have to change KV in Riak Core a bit because in KV the key that we hash on and the key that we write to are identical, whereas in Time Series they're different. So there is some plumbing there, but substantially Time Series is a library on top of Riak KV. And there are some more complications to that. It's not as easy as it seems. There's because a lot of things turn out to require to understand the function of your keys, so anti-entropy and things. But as very much as we can, we try and keep those separate. So we all know that KV stores are literally very, very dumb. They don't know anything about values, but we need to teach Riak. If we're putting structured data in the value onto the disk, we need to have a mechanism to teach the cluster about the structure of that data. So we define structured data with a data query language. It's a create table function. It's not strict SQL, and you'll notice there's some things a bit odd about it, but it looks like a recognizable I'm creating a table statement. It has a number of fields. The fields have type. They're named fields. They have types. They can be null or not null. The types are, 64-bit integer, double, timestamp, Boolean, and a sort of varchar binary one. And we have a key structure that tells us a two-part key. One says how to partition it, and the other says what to write on disk. So you have a two-part key. And what we do with that is we have a LeaksYak parser compiler structure. We push that statement through, and it emits an Erlang data structure, which is the record that describes a table. We distribute that data structure around the cluster with Riak Core as Riak Core metadata. So the entire cluster now understands that a table has been created and it has this structure, it has these fields. And then we use Richard Carlson's Merle to generate a dynamic module that can destructure the data that we're writing. So we then load that module in, and it's the module name has the table name in it. And so now magically our cluster now has loaded into it programmatic Erlang that can destructure data without Riak itself having to change. It has a simple call point, and it knows that depending on what table it was, it can turn the table name into a module name and then call the API on that to get fields, set keys, generate keys, pick out the fourth field, check types. All the information that is needed throughout the cluster is now available programmatically. So we try and make, we actually teach Riak about the data that we've defined. And we have a distributed query system. So you connect to what we call the coordinator. That's whichever. Riak is typically organized as an agnostic cluster. Any machine can. Generally, no machine has a special function. Sometimes for certain things on Riak Core, one machine is nominated as the coordinator. But for the query system, you can connect to any machine in the Riak cluster, and that machine will run the query for you and act as a coordinator for that query. So when I create a new query, my coordinator will run an init phase. It will take the query in, it will exit, it will parse it, it will validate it, it will do whatever it requires, check that it's a valid query. It will then ask, it works out where the data is based upon the key that you're doing. It sends its requests off to some nodes, which may be local or may be remote. They will read some data, maybe process it, return it back to the coordinator, which will do a finalizing process of it and return it back to the customer. So it's very generic distributed system. And I'm now going to talk you through a bit of that pipeline. Again, there's nothing fine or fancy in the SQL processing pipeline. In this case, obviously the pipeline varies. If it's a create table query, is different from a select query, but this is a select query. We typically, somebody requests, sends a query to us in SQL, we then compile it into an internal data structure, and then we have to do a series of validation checks. We have to say, does the query refer to a table that's actually in Riak? Because if it doesn't, you won't get an answer. And if it does, do the fields in the query match the definition of the table? So we first of all check that. We use this function, this module, the helper module that we've generated up here. We can use that. That has all the functions required. You can say, does this field exist in this table? Yes or no. And if you get an error, you chuck out. We then say, have you given us enough information? Because we still need to know where in the ring the data is. So have you given us enough information to send out our subqueries to get the data? So it's a valid time series where clause. And again, we use the helper function for that. Maybe return an error. And then we have to go away and say, if it's a calculation function, the calculations are all typed. You can't take the average of a varchar. So we have to say, is it a type safe query? Is it going to calculate correctly? And again, we have an error. And then finally, we validated that we have a complete query, and we then send it off to a query rewriter, which will actually execute and run our query. And what we're doing is we're using the decorative properties of SQL to generate subplan queries in SQL. So if we have here a typical time series query, which is a select clause with a function from a table with a key that has time quantization, and we take that function and we typically unroll it into multiple subfunctions which roll back. So let me talk you through how these things work. My coordinator is going to send out over the network to two separate vnodes, two separate queries. I have in here a time period which crosses two quanta. So I know where my quanta barriers are, so I'm going to one vnode and saying, right, give me the piece of data that you understand that matches this clause. I'm saying I want the average here, so I'm asking you to sum the temperature here and count it, and I'll use those two figures. You're going to give me two figures back, which I'm then going to process here. I'm going to turn that into a computational average. So I've transformed my average function, and I'm going to repeat that twice. So this says go from the start point to my quantum boundary, and this says go from my quantum boundary to my endpoint. So I have a time slice, and I've distributed my work. And to make it easy to understand and make it easy to debug, we use effectively we take a decorative SQL statement which has SQL syntax, and we rewrite it into our own runtime statements that have the same structure, they have the same clause of the same names, and we transform the syntax to make it executable, but we retain the semantics. So it's always pure SQL. And typically what we do is we express all these clauses as what we call in the trade YASL, yet another shitty Lisp. We knock out little Lisps, and we then have executing things that run those Lisps against data sources at various places. So decorative SQL, which maybe have execution hints, and we turn that into a query plan, which is a series of executable fragments with a transform syntax, preserve semantics. So if you look at SQL clauses, they have a very common and standard signature that operates. And if you imagine that your data on disk is written, it has a series of rows with values, and it has a column description for each row, which has a name and a type. And you typically take a pattern like this and you operate on that. And that normally obviously starts on disk. But and a SQL query will then return to you a series of values in columns with a column name and a type, and it will have transformed. It may have increased the number of columns, or it may have reduced them. It may have increased the number of rows. It may have reduced it. It may have transformed the types. It may have da-da-da-da. But all of them perform to this generic structure. So what we're then able to do is we have an executor that runs and executes all these Lisps, and they all have slightly different behaviors, but we're not quite here yet, but we're moving towards a world in which we have this distributed executor that you can just pass in fragments, and it will take the same thing. It takes typed and named columns and a set of rows, and it emits typed and named columns and a set of rows. So a very common structured standard signature. So that's basically what we're trying to reduce all this processing complexity. And select is a row and column operator. As only operates on column type. There are row operations, there are column and row operations, there are header operations, but they all have roughly the same approach. So so not only are we using SQL as a way for end users to understand how the system works, we're using SQL as a way for developers internally to understand how the operation works as well. And the executable fragments are, as I said, shitty Lisp, so they tend to be a tuple, what sort of thing it is, and then a list of operations that you operate on it. So that's an AND operation with some operators, and you then have a runtime that takes that, and you pass in your rows and columns, and then it knows how to just run and execute that against that. So lots of YASLs. We're trying to smooth our YASLs out, make them more interoperable. So how much SQL do we have? We have select well, we have a group by, order by, and limit are being worked on for the next release, and we have a number of functions: average, mean, max, sum, count, standard deviation. So you can now start putting data in. You can start having structured keys, and you can start building quite sophisticated stores of data that you can then operate on. How much longer we got? 10 minutes. Okay, cool. And when I'm talking about SQL, I'm saying it's a decorative language, but it has execution hints. And what do I mean by execution hints? So straightforward SQL, that's decorative. It says get me this data from my table. If I start doing things like limit, then limit kind of looks like a hint on how you should execute it. Give me the first 1,000, or whatever. And we can extend that by by adding our own custom clauses on the end. So if we have to do things like harvest and yield, and we want to specify how we would like the query to execute, what degree of consistency the data we want comes back, we can simply extend the end of our query language by adding custom clauses. And typically what you do with that to make it operationally easy for tooling is that your standard SQL would work in tools, and then the execution hints you want, you would normally set as table default. So you can just use normal tooling with it, and you can say on this table, I expect you in normal operation to run it in this style. And if you need to overload that and replace the execution hints, then you can do that if you have higher consistency or low consistency requirements. Okay, so what does the future look like? Obviously, I wasn't allowed to come here on my flying unicorn and park it outside. I had to come by plane by everyone else, but we're trying to look at a range of interesting things because we're using the time structure of data as a way to collocate it to give us this wider range of queries. And we're looking at other mechanisms that we can use to collocate data, and can we then use the same query structure on top of that data. So the other sort of collocated data we have is CRT Sets. That looks like collocation. A set is well, it's a set. You put a number of things in it, and the way that currently written in Riak is that you have a key that points to the set, and then you add and remove elements from that set, and those are executed as at the moment they're written onto the disk as a binary store, and they're then read off the disk, and there's a library that operates on it in situ. So this obviously has performance issues. If I have a CRT set with 100,000 elements written to disk, at the moment to do reconciliation, what CRDTs will do is they will send that entire set to replicas, and they will then do merge operations on the two sets. And they will, to actually add an element or remove an element set, I have to read 100,000 elements from the disk, operate on the set in memory, and write the new version back. So I have a lot of I/O, and I have a lot of network cost. Russell will be talking tomorrow about the work he's been doing to break that up, where the set is written to a disk, and you can read and write an individual element, and you move from state-based to ops on CRDTs, where the whole object has to be swapped around, to delta-based, where you can send a causal fragment that says, I have done this operation on it. Can you do that same operation? And he'll be presenting the work of the tremendous transformation of that in time, in speed. So if we have performance sets with big sets, then we can treat them as we can start treating sets as queryable things. And we've done a couple of experiments using existing CRDT libraries, which give us non-performant but indicative. We can show that the mechanism works, but it won't perform for customers until we get the big sets in. But effectively, what we have at the moment is we have a table schema, which is a series of column definitions and types, and then we have sets of rows. Those are our core data elements inside time series. If we stop treating CRDTs, I kind of think CRDTs are going to be like OTP, which no longer stands for Open Telephony Platform. It just means something. CRDTs are convergent replicated data types, and when you look at them in this way, they stop being data types and they become mechanisms for managing causality with data underneath it. So I think the DT of CRDTs will just become letters. But if you look at it like this, you can use CRDT maps as a mechanism for expressing a data schema, and you can use sets of maps as ways of calculating, of handling rows and rows of data, and you can use the sets to represent that. But what's quite interesting, that's very boring. What's quite interesting about the CRDT work is when you actually look at the data that you can model with maps and sets, is you can start modeling table joins. You can start looking at much, much richer data structures that are eventually consistent. And it turns out there's quite a lot of application complexity that now becomes possibly eventually consistent, and you can start using maps that contain sets, that contain maps, that contain sets, that contain maps, that contain sets to represent multiple table joins. And at that stage, then we think that using the sort of time series query, the time series query language stops being about time series. I mean, it is designed as an architectural query approach to allow queries to be run against collocated data. And if we can get the next phases in, then we think we can really move that query language along in a way that takes us just out of the time space. It has to be said that this is future stuff is not a company. This is not a company roadmap, right? This is us attempting to understand what that world looks like. I've got 5 minutes left. So you still have the same problems. You either talk to all servers or you talk to 2 servers. You still have a data access problem. And one of the things we're thinking about, can we steal some of that causality information that is used in delta-based CRDTs and use that to build eventually consistent indexes? And that's to say that that's a research project is overstating it. I have a feeling in my stomach that it can be done, but I have got no evidence that that's not anything but bullshit. But I understand the laws of physics. I think that can work. So we're kind of like, I was told at Basho that ending a presentation with the word "dunno" is probably is not. I suppose the difference between Americans and Scottish people, isn't it? Americans will end up with rah rah rah, and in Scotland you end up dunno. But yes, there's quite a lot of interesting stuff about, can we broaden out this query path? Can we solve this problem of the KV problem of all or nothing querying? Is what we're really trying to break down. Can we have a bit more than nothing and a lot less than all? Is where we'd like to go. Any questions? It depends on what they are. They're a mixture of, at the moment, more happens at the coordinator than we'd like, and each iteration, we're pushing work to the edge as much as we can. So some operations we do the work clause at the edge, and then we do most of the other stuff in the coordinator. But each release we go through, we optimize that work to eliminate it. We're trying to push as much of the operations to the edge as possible. No, we don't. We don't do that. The data is structured so you understand it, so you can access it through SQL. We don't. We don't let you run. No, no, not yet. Oh, sorry. The question was: is it possible to define your own functions and then apply them, roll up and execute them at the V node, which is not there yet. It's something we have thought about, but we haven't got there yet. Any other questions?
Yeah, so question about, so your theory about the CRDTs was an interesting idea. How's this going to play out with performance, right? Because you tend to solve the anti-aliasing of the data, but you presumably create a lot of space in between, and you've got to pattern match on things. So how's this going to affect performance of the system?
Well, I mean, Ross will be talking about most of this tomorrow. I'm not going to pretend that I'm a great expert on that side of things, but by breaking up the CRDT into individual components, you get your data access pattern is much less, and actually I don't know how the AE works. I have read Zishan's paper on it, but you probably need to ask Russell on that. But the performance, I mean, the initial performance indicators are really good, aren't they? The big set stuff is a lot quicker than the monolithic sets.
Okay, so you're actually saying at the moment you believe you're going to get performance improvements.
Yeah. Tomorrow, on the big stage, Russell's got all the... I don't want to steal his glory.